Good morning. This is the second day of our colloquium, and today the sessions begin with Dr. Professor Sandip Dhara. So, Professor Dhara is the head of Science and Nanoscience, Surface and Nanoscience Division, Indira Gandhi Center for Atomic Research, Kalpakkam, and Professor of Homi Bhabha National Institute. He took his PhD from National Physical Lab in 1994 and joined IGCAR in the year 1996. He is a fellow of Royal Society of Chemistry. Professor Dhara was a visiting professor in University of Valencia, Spain, Technical University of Chemnitz, Germany, and Institute of Atomic and Molecular Sciences, Academia Sinica, Taiwan. He was associate professor in Electrical Engineering Department, NCKU, Taiwan during 2007 and 2008. Dr. Dhara has published more than 300 research publications, which include several review articles and 2 book chapters. He has delivered more than 100 invited and plenary talks. He is the recipient of Homi Bhabha Gold Medal 2019, BAE SRC Outstanding Researcher Award for 2012. 5 out of his 6 PhD students received Homi Bhabha Gold Medal for Best Thesis Award. Dr. Dhara is specialized in studies of light matter interaction in the field of near field scanning optical microscopy and tip enhanced Raman spectroscopy. Yesterday, Sir was actually took a class on quantum confinement phenomena in semiconductor nanocrystals. And today, he is actually moving to another interesting topic, nanoplasmonics, metal nanoparticles, metal dielectric nanostructures. Now we are slowly entering into the various aspects of light matter interaction. So with this small introduction, I welcome Professor Dhara for his lecture.
Yes, thank you very much. So my affiliation is missing, but anyways, Professor Dr. Potti has introduced. So you must be knowing that I am from IGCAR. Kalpakkam, and also a faculty of Homi Bhabha National. I have just put my video off so that quality is better. So now, as you know, I have out of 6 students. 5 is the gold medalist of the university, and as you probably know, if you go to the Nature Index, we are the topmost. We are the best institute now in India in physical science. So, and one of the student is also the attendee, Dr. A.K. Sivadasan, who is also one of my prize student, who is serving Kerala government and the students there. I hope that a lot of students are getting enthusiastic with him to take up bigger challenges. The kind of background he came from and the performance he made, he could have done even better had he not relented to the for other things, and he has to have his livelihood. So he has to join some job early, because he is from very poor background. He was from very poor background. Otherwise, he would have been a marvelous scientist had he continued his postdoc and all this. With the brief these things, I have already thanked the organizers for giving me importance and giving. Of course, I have chosen the 2 topics. Of course, I was thinking that it will be converged to a single topic, and I'll give a single talk. But it became I didn't know that it will be 2 talks. Like Professor Vijayan is also giving another talk. So it's good that I would split and not to run my Rajdhani Express on the head of the students. So yesterday I very relaxed way talked about a very difficult subject of and actually philosophically I introduced. I must say I have not gone very analytical, and it is not necessary for such a public lecture to go very analytically solving the equation, solving the integration and all those things that the students themselves can do, but or the teachers are doing. But what we can give it a larger context, how the subject means to this. So here, of course, I will not promise that level of nanoplasmonics, but nevertheless, I will more emphasize on the applications, various applications of this subject. This subject is in that way, I must say, it's not very rich in physics. So that's why the application comes in mind in the but it is nevertheless one of the most, if you see the abstract, it is one of the greatest discovery of last century, which has made the life so easy. As I go along, I will make you understand. So next transparency, please. Yeah, so I always like to give this feeling, but what happened when you reduce the size? So that is the first question was seriously asked when nanoscience came in. We tried to establish nanoscience as a subject. The best example is always given that if suppose you take a say you think of this is a gold cube, which you know all that gold is a material which can be cut very easily, and it can be cut in the micron level very easily. I mean, most of our goldsmith play with my few hundreds of microns threads in their daily work. If you see the sophisticated work, I don't know about Keralite gold jewelries, but in Bengal jewelries, there are plenty of example of having threads of few hundred microns of the order of the hair and all. They're making decorations on the ornament. So now if you take a 1 meter cube of a gold, and if you think that is a too big a gold and to be rich, so you think of a butter of 1 meter cube, and you start cutting it by pieces. Like you go to the Rubik cube level, and then you go to the sub-micron level. Now, 0.1 mm is roughly 1 micron. So now, roughly if you mind the micron level, now in the micron level, if you go, and now let us assume that this is gold. Now the question was asked whether what will happen to this gold, and this has been understood very nicely from a theoretical study and then also experimentally, that its melting point comes down drastically. You see, melting point is normalized with the other temperature, and then they have with the bulk melting point. See, is the melting point of the nanoparticle divided by the melting point of the bulk material. If it is normalized to 1, so then you see once the particle size reaches around 25 nanometer or something, there is a drastic drop, and the melting point goes like anything. If you deal with gold nanoparticle, normally gold is boiling point will be how much, melting point will be how much, more than 1000 degrees centigrade or close to 1000 degrees centigrade, or more than that, I don't know. But it goes down to 200, 300 degrees centigrade. You can melt them, and at least the surface you can melt and do a lot of physics or growth, nanostructure growth on that. So the reason was easily understood, that are normally understood. Of course, it can be understood in the atomic level with the proper atomistic calculations, but just simply to understand, your surface to volume ratio is very high. You see, is 1 meter cube surface area is only 6 meters square. Now, if you just take the surface area, if it is 1 micron, and if you go to that means 1/1000th of a meter, 1/10,000th of a meter, then you see that the total area on the surfaces of, if you add all the nano microparticles, then it will be 2.5 acres. I don't know if acre is understood there or not. It is of the order of 10 to the power 4 meters square. So just it goes 4 order high. And this surface to volume ratio, because the surface is a source of energy. I'm not going to the subject today. As everybody know, you create surface, actually you have to spend energy for the surface, and automatically volume comes up. Try to think about it, all students, that surface is if you can create, you have to spend energy for the surface to get a volume. Volume is the net result of a creation of a surface. So whatever we spend energy for any material is for creating its surface. Volume or the amount of the material is automatic gain out of it. So that is a next transparency, please. Now next. Now I'll go to the plasmonic subject. So you see, if anybody has read this abstract, I have started and I have gone almost along the abstract. So that, and the abstract I wrote in only 10 minutes because I was already very late. And for different reason, I could not respond it in the proper time, so I had to promise. And there are some mistakes I have tried to change them in the abstract. But in the abstract, I told that actually nanomaterials started its journey, or nanomaterials, so-called, started its journey along with Michael Faraday, who is the discoverer of electromagnetic theory. It's very interesting that both electromagnetic theory and nanostructures, which is being covered today, is actually coupled together. So it is good that it is a good respect to that great person. So it is about a Lycurgus cup. You have seen, this is the 4th century Roman glass, which is like our Kohinoor is now Kohinoor diamond. It is, or others along with other things. It is now in the British Museum for some historic reason, or of a correct reason or wrong reason, whatever it is. Now, if you see this light, beauty of this Leica gum is that inside, if you give a light, it becomes red, and outside it, you shine the light, which you are seeing, it is green. Structures are okay. Now, this was a big puzzle to the British, and Faraday solved it. Faraday told it is nothing like that. I don't know how he got this idea. He told there are metal nanoparticles of different size given in different layer, and those metal nanoparticles, and he made metal nanoparticles by electrochemical technique, and showed that these colors can be achieved by the gold and silver nanoparticles. And also, you have seen, being in Kerala, particularly when I visited Kerala or deep in Tamil Nadu, I have seen many churches is having this beautiful depiction of the different parts of Jesus. That many of them, not all, of course, are in the glass. And as you know, that these are not basically very old object. The night lamp I have shown you, it must be in few hundreds of lakhs, or at least few lakhs it will be. This is this color, whatever you are seeing, is basically, this color is not the color. This is not a color is used here. It is all metal nanoparticles inclusion, so that these beautiful colors have come. And this is called stained glass. So stained glass is, that's why it's so very costly. So metal nanoparticles, when you reduce its size, not only changes its material property, the mechanical property of, or whatever thermal property, but also changes its color. So what happened there is the fact. Next. Yeah, so that is, everybody knows, of course. I was making so much of stories and all, but everybody knows by this time, even the kids knows that if you have a metal nanoparticles whose size is comparable to the wavelength of the light, and as you can see that is being a metal nanoparticle, you have large number of carrier, free carrier available, particularly that's why its noble metal is known. But nevertheless, as we build up the subject, then you will understand that nowadays even semiconductors with large availability of the carrier above its conduction band, above its Fermi level, that means in the conduction band, that means you can populate your conduction band very large, in very large number. That means with a heavy doping, that means taking it to the metallic regime with the all semiconductor properties. Then there you can also start seeing those activity where electromagnetic wave gets confined, and electromagnetic gets confined along, because this is a small dipole is created, and in that dipole it interacts with the natural dipole of the electromagnetic wave. As you know, it has the electric vector, and they get coupled, and the strength is enormously increased, of the order of 10 to the power 4 to 10 to the power 6 times. That exactly what that is the order always we see in the changes in any scattering phenomena, including Raman. So that's what we are going to take up one by one. Next, please. So that is, of course, just a glimpse that when electromagnetic wave get close to a nanoparticles, it get coupled, and it strongly coupled, and there are a few phenomena occurs. Of course, we will not talk the intraband phenomena or interband phenomena, where actually Dr. Sivadasan has phenomenal few words. And we are not going to that topic. We are going to rather a popular topic. These are all more subject. Of course, it has a use. It has its own use, but very limited. But it normally goes in the normal understanding of the physics or some other phenomena which are not forbidden phenomena, which we can explain it. But we'll try to understand where we can understand things better in the daily life, which is the radioactive decay. So there are also radioactive decay. That's where photon and all those things comes in play. Next, please. That's what you see, the light and all. And as you know that the plasmon frequency of the nanoparticles, yesterday I forgot to give this formula, where you see directly proportional to the root of n, that means carrier available. So naturally, large number of electrons availability will largely make this omega, that resonance frequency. And this resonance frequency is also controlled by your the dielectric medium of the system, that is whether epsilon of the material and dielectric. The metal and dielectric are real part of the dielectric is also this part has to be 0 to get the resonance. Next plus. So now, as you know that there are a large number of implications, and when we always told that metal nanoparticles, particularly gold and silver, is I'm not too particular about going about particular of these materials, but just in generally I'll be talking. As you know, gold nanoparticles show the surface plasmon resonance for a single peak normally, but if it is elongated structure, then you start getting another peak also. So this gold nanoparticle peak is the first peak, where around 500 nanometer, that is the signature peak of gold. But nevertheless, gold, as it has an intraband contribution, that is what I was telling, that physics reached there. Silver is normally at 410. Normally it is not changed. Silver, to my knowledge, it has no intraband contribution. Not that is for fact, but to my knowledge, it does not change its position drastically. To change the color, actually, gold is mostly used. Silver, normally the strength, the intensity is very high always, and so silver is used for very strong intensity of the particular color. 410 nanometer, you can think of it is around close to blue. Correct, if I know, yeah, this is correct. So close to blue, and then if it is red, if you want to encompass the whole regime of the visible band, then gold is the only solution. As you see, 500 nanometer, and if you can change the aspect ratio of the gold, you can reach nowadays we are making this in our lab, so it is, you can go any amount, 600 to 700, and even it can be, nowadays we have reached even 16, or in this topic it is not discussed, around 1600 nanometer deep in almost near IR you can reach 1600 to 1600 nanometer also you can reach, near IR you can reach. So you can have a large control on the it is from blue to red, you can go. Next please. Now, using this different like you see, I told you about 650 nanometer, 750 nanometer, 800 nanometer SPR, and we did the surface enhanced Raman spectroscopy. If somebody knows about surface, just to brief what is surface enhanced Raman spectroscopy. Normally, Raman spectroscopy is a very weak scattering phenomena, very weak scattering phenomena. Remember it. Normally, it is very popular, but it is very difficult to get. In fact, Raman had to wait for his Nobel Prize till the laser came in, because laser only increased the more probability of the scattering and seeing the phenomena. But nevertheless, when it is a batch process in a pharmaceuticals or any kind of a medical purpose, then you can understand you have an enormous problem of getting the proper signal from a minute number of inclusion. So to do that, we normally take help of the same metal nanoparticles, gold, or for that matter, dielectric also come in. Dielectric means heavily doped semiconductors are also coming in nowadays, because sometimes metal inclusion is invasive, but whereas semiconductors with large band gap is not that invasive to the biological system. And there you confine the light and increase once you confine the light, the Raman phenomena increases of the order of maximum. I'll give you example of 10 to the power, I'm going a bit slow, 10 to the power 8 times. So here we could show that we could even detect up to 10 to the power 6 molar of a particular reagent. It's called rhodamine 6, which is all normally taken. There are methylene blue is also taken. They are very less responsive to because we cannot play every day with the biological samples, which requires license. But R6G is also very dangerous carcinogenic element, but we take precautions to handle it. And this scattering phenomena is very low without that. Actually, we should have shown without any SARS effect. Now is with gold nanoparticles or gold nanorod in this case, with using different surface plasmon peak, we could detect up to 1 micromolar. Next, please. Now, next is even more beautiful. What we did that we have used also another nanoparticle, 650 nanometer only we choose for specific reason, because if you see the 650 nanometer nanoparticle. Then we saw that there is one 527 nanometer, that the radial part, breathing mode, is very intense and very narrow. With that, we did the resonance. So this this resonance with, sorry, 650 nanometer itself they have used, and there they saw that resonance of the R6G peak is 527 nanometer. And here we can go even 10 to the power minus 10 nanomolar. If you see the red one, 10 to the power minus 10 molar, we could go. This is, and we did also one of the Raman modes, a 1648 Raman mode. We have used Raman imaging. That means how we do, we scan the whole area with a particular sector and measure the intensity. See this second V, image V is showing the image color distribution, and the color distribution according to color bar, yellow is the strongest, and you can see it. And all others are different color, and you can see this is a 3D image. The number C is the 3D image, where you can see even a small molecule, single molecule area is that area will be very small. Single molecule is observed. They are in that yellow peak here. That is the strengthiest peak. So single molecule is imaged there by the SARS effect. So just confining the electromagnetic wave using 532 nanometer laser. We can, because the molecule has a resonance, you see that is the inside peak is the absorption peak for the R6G molecule. Then the 527 nanometer matches with the 532 nanometer. So that resonance actually, with the help of the SPR or the surface plasmon resonance, which is also very closest, we could not get anything near that. Of course, we have 500 nanometer peaks are there. So with this, we could get the single molecule imaging or detection. Next, please. Okay, so same another example. I will not dwell on this subject more, because this is, I always respect this paper, because he first showed that the surface enhanced resonance Raman spectroscopy can be tuned with the shape of the nanoparticles. In this case, silver and gold is coated together. And this is a very famous Murphy's group. And one of our, he's my junior and my friend also, N.R. Jana. You may know him, that he's the editor of ACS Nano. And he is nanomaterials. He's one of the potential researcher in this country, whose citation once upon a time was the highest, and probably today also is the highest. He is in the ACS. Next, please. Next transfer. So they are, it's a biological example of how the SARS effect can be used, even analyzing the tumor growth for a particular, you can inject a particular vein or artery, I don't know, to go to keep these nanoparticles to the area of the tumor, that doctors can take a decision. So one has to do work with the hand in on with the, and then once the nanoparticle goes there, so over time you can see that how the intensity is coming, or particular component of the, I am not going to the subject, or I don't know the subject, but you can have the reference and can read it. The tumor growth in the mice cell has been studied by us. Must be there are more important. This is all 2010 subject. I have not updated myself, because I am not working in this biological detection. So somebody can go into it, and people are in the mice, you can easily study it. But nevertheless, this is not the best technique, as you are injecting the metal nanoparticles. As you know, above a certain limit, this is also poisonous. Though people say that gold is not poisonous to body, it is actually absolutely wrong. It is to a certain extent, it is less harmful. But remember it, many times we consume gold in different way. In Ayurvedic way, there is a limit, and you cannot take as much as you can normally, because in many sweet we use silver or gold as a foil, and this is not always advisable to take it at the large level, to my understanding, because gold is also used in foils. I have seen in some parts of the sweet makers use it, very costly gold foil stuff, which are submicron or micron level thickness gold foil, like silver foil, which is plenty observed in cashew burfi or something. Just be careful. And next, please. Okay, so nothing. So spin plasma. I'll give few more example. Next, please. not going to that, but it's slightly different subject which has not been covered there, but I just will tell very briefly. This was actually, we had published this work, this first micrograph and diffraction pattern, TEM micrograph, and you see that there is actually some small dots are embedded in a nanowire kind of thing. It is 50 nanometer diameter at the most. This is actually silica nanowire, SiO2, and on his gold is embedded. I forgot to include my publication. Actually, I published along with this group and in advanced materials for this. When I was there, one of the students made this material, and I converted that work in a advanced material paper way back 2004 or 2003. Yes, after then I gave subsequent lecture on that time. My interest came in the plasmonics, and I gave few lectures. I went visited that IAMS, that is what Professor Prof was telling, Institute of Atomic and Molecular Science, and then showed about that how plasmon can be used for confining light. But they are very intelligent and very hardworking batch of students are working there. 20-30 people are working in a particular group. It's the American way of approaching to the problem. 20-30, some 5 postdocs, so you understand what kind of energy they can put in, and every week they meet to come up. And anyway, nevertheless, using these nanostructures in plenty, they made this kind of bridges. You can see that this is the microstructure of those bulk ensemble of this nanowire, gold nanoparticle embedded gold nanowire system, and then they are made contact in both sides, and then when they shine the light of 532 nanometer, which is the resonance peak of this gold nanoparticle, surface plasmon resonance of the gold nanoparticles, they started switching. So it can be easily used for optical switching. Next, please. It has been later on published in Nature Materials, and then subsequently in 2015 I visited again, and I also demonstrated. I made some structures by ion beam technique. Yesterday I was talking. Dr. Raghu from the director CMET-Thrissur was asking me the question how you have made the sample. These samples are actually very intriguing. That will take its own subject. This is a material which is made not by even annealing. It is by, we have annealed it by another ion. This is the bottom is the silicon ion. You can anneal metal nanoparticles by another ion which is not miscible to that system. So gold and silicon is not miscible. So or very high energy silicon is used to make these gold or silver nanoparticles bigger. By impact, during their impact, local thermal conditions can help them to grow these nanoparticles. In fact, beautiful examples are there, not from my group, but some other group. Okay, so now and there the beauty is that because you have this thermal treatment can spread the region of the distribution of the nanoparticles throughout because thermal diffusion would have taken, but because by the ion beam you have the localized diffusion coefficient will be very low. The heating will be extremely localized and very quick, few microsecond or few nanosecond they are interacting. So the gold nanoparticles will be in the same one particular layer of it, and then if you can connect to that layer, you can easily find out both sides. You can do the ion milling. We did the ion milling of the both side of these facets, and then we did the metal contact here. As that's you see that this is actually it's a top cross section image. It is not a top view. It is a cross section image of the as you can understand has gone to the depth of the system, and silver and gold nanoparticles are somewhere in between. And here you can ask the question, silver you told that 400 nanometer is the this thing, but interestingly second harmonic generation was stronger than the primary, and that's how this paper is all about the second harmonic generation. So I'm not going to the I'm also going to touch upon that topic, that even the localized interaction is so strong that you can even generate second harmonic generation, second harmonic. Go to the next one. I think I have given some example. Okay, this is the plasmon activity. Next, please. Yes, I talked about the second harmonic generations here, not very explicitly. Actually, this transparency is quite busy, but I'll do it. Please stay there. And it is it is a second harmonic generation example, sir. But unfortunately, I forgot to include the reference there. But all references are there in my paper if people look into it. But you must understand, and it's the visual example. I think it's a science paper or somewhere. The visual example how second harmonic hotspots have been also created in this technique. So if you make a metal nanoparticle and can focus a light, and if you have a technique, because near field, it is some near field imaging technique by which they have created, they have showed that the primary hot, the middle one, and also top and bottom, they have created the second hotspots corresponding to the second harmonic generation. It is so strong that in fact you will be astonished to know that even with 400 nanometer, it didn't get the sufficient conduction or sufficient conduction in my previous structures. In fact, when I used 800 nanometer, because of the second harmonic generation, because harmonics, so frequency will be, so 800 nanometer, so frequency will be lower. So wavelength is 800 nanometers, so lower frequency, so we could get that connectivity very promptly. Second, another example, that's why I told you it is very busy and I could not make it. Actually, I must be very apologizing that I started this presentation yesterday after my talk, and then I saw that there are some issues and in between official matter came, so I could not do this. So this is a second example, the first bottom block here. Okay, I can use the transparency here, probably this people can see, right? Here, the plasmonics is even used. It is actually can be seen a very nice review article of Atwater and Paul Polman in Nature Materials, where they have told even gold nanoparticles are nowadays used, gold and silver nanoparticles are used in layered structure for this photovoltaic, where it can be used as a good absorber. So if you intelligently use it is of course the review article is 2010. You understand now this is in the applications, must be in the applications, in the advanced applications. There you can solar concentrator. You can normally there are many approaches like you have to do anti-reflection coating so that light goes in, cannot come out. That's called anti-reflection coating. Then also you can use the natural, because the major part which is lost in the solar spectrum is actually in the visible region. That is very unfortunate. So because that gets reflected and that comes out very easily. So that part you can use as an absorber. So if you can introduce a layer of metal nanoparticles and wisely, because as you know that it does not encompass one particular size, does not encompass the whole spectrum. It is only SPR for a particular peak, for a particular size. So you have a nice size distribution where you can absorb the whole white band, whole band of the visible region. This will be fantastic. But there are other issues, because light is a good scatterer. These metals, but nanoparticles are also good scatterer, so that it has to be taken in a particular layer where absorption can take place, and before that the light should go inside the system. So you just cannot blindly put it on the top of the surface. And the last example, the last frame is the most interesting frame, which every day we use, but we don't know. That is to signature of life. Every human being, I mean, when we plan or when we detect the pregnancy test, the SPR is actually, we tell pregnancy test for very positive is basically used the surface plasmon technique. Actually there the strip is having a metal nanoparticles, and when we use the probe molecule for this particular test, then if there is a life, then the live motor molecules can sit on these nanoparticles, and they can make the cluster, instead of this nanoparticle being individual or monodispersed sort of stuff, they can cluster these nanoparticles minutely and can change the SPR. So that has been monitored. That must be some calibration is there. With that, the motor molecules are coming and sitting on these nanoparticles, and they coagulate them and change the SPR peak of the particular strip, and that SPR peak is taken as a signal for the signature of life in the probe. So that is regularly we use it for our life, in hospital every day they are using it. So this is, we must be, the people who are working in nanoplasmic must be proud of that. This is something which is used by the poorest of the poor even. Thank you. Next, please. This is the second harmonic generation I was talking. So I already told, but people can pick up the, because this is a subject which is very interestingly taken, and where they were, actually this is a subject for the nano antenna. So you see that nanowires arrayed in a particular way, particularly the nano wire or nano rod. If you can, I mean, when people do this lithographic pattern on the materials and can get a particular signal in a very efficient way. So these are used in the nano antenna technique, the second harmonic generation. Next, please. Next. Okay, so this is even, as I told you, no, previous. Okay, I'm late, but still I'll just tell you, this is even nanoplasmonics are used to even bending light, beam splitting in the micron or nano level. It is a engineering subject now, Y splitter, Mach Zehnder interferometer, all these are all nowadays in engineering regime. That's what I told. Physics is very less. Physics is very small. Maybe the one topic was there, that quantum electrodynamics, probably there, probably it will be dealt, which I don't know the subject. That is the only narrow subject. I don't know who is covering that, or at all it is being covered or not. So that is the subject where it deals. Otherwise, this is a very engineering. All engineers use is this nanoparticle and used for different devices. Thank you. Next, please. Now going to the another subject. I'm already very late. Okay, I'll just briefly tell. As you know that that is called, you cannot send light through a small hole, or you cannot really think that light will come between, like you have a material in the, is, you know that in any material is made of some element, say carbon. I'll take a carbon foil, and now 2 carbon atoms distance is around 4 angstroms, say. So that is a unit cell. So light can come through it. It is not so, right? You cannot make a thick block of carbon carbon. I'll give a crystal material, perfect crystal, so that light can light come through that 4 angstrom thickness, because unit cell is 4 angstrom. There is a gap between these 2 atoms. Whether light can pass through it, not necessarily. Even if I make thinnest of the thin, then the question can come, perhaps. So light is restricted. Actually, if you see the numerical aperture, you take n theta is the numerical aperture, n sin theta as the numerical aperture of the material is the capability, how much light that is the refractive is related to this related to the refractive index, and in which angle the light is being incident, and all those things. So if you assume sin theta is equal to 1, that means normal incidence, there also it will be maximum 1. And you can see that means lambda by 2 you can is the limit. That means if you send a light, if you have a light of 500 nanometer, you can think of, in microscope, you can maximum think of lambda by 250 nanometer, you can resolve it with a lot of trouble and lot of difficulties. Now, the question was, that is, but now you are talking of a nanometer of 200 nanometer, 20 nanometer, 10 nanometer, and many times you are talking of a bacteriophage. That means it is mostly used for the biologist, because this is not a demand which came for the material scientist. Material scientist is very of late want to know behavior of 10 nanometer is different than 20 nanometer and all. These are all 20, 30 years question. The 20, 30 years science is not 20, 30 years old. The question was the biology or the medical science has evolved much earlier. They wanted to see a bacteriophage activity at the dynamic level. That means what he's doing exactly on the cell. That was very difficult to observe. So they have to do a cryo-TEM. That means you have to image it out. You have to do it in the cryo atmosphere. You have to do that reaction and freeze this in the cryo. That means you can have to pour liquid nitrogen at that moment, then take a cross section of that thing, and then you will go back to your TEM again to see what exactly how the bacteriophage is. So, and that has to be done in correlation, autocorrelation, a lot of mathematical modeling, a lot of uncertainty was there. But now with the help of, now I'll be talking of the subject. Next, please. Oh my God. So next, please. So we'll not go spend time on that. Next. Here also I'll not spend. I already have talked. Next, please. That's why it is not very urgent. Yes, I'll give you this example, and then I'll go quickly. If you, this is the light line. You see this. This is the angular frequency and wave number. Now, if you use the normal light line, will be say 500 nanometer light. If you see the frequency versus wavelength, if you E is equal to h nu, energy being constant, you can see that this is the frequency, and then you can see this is the normal light line. Now, if you thin down the, suppose you would have, sorry, if now you try to force the light in the narrow path. So what you do is that, suppose you are doing 500 nanometers, so make a hole of 250 nanometer and try to see what will happen. 250 is quite above its lambda by 2. 200 nanometer, it is 250. So if you do it 250, for all practical purpose I am talking, then you see the light is coming out, but somewhat in the diffused fashion, and the light is it will be little bit slow. So it is called evanescent. The light will try to die out. It will not reach far up from the hole. It will die out very close to the hole itself. But now, do one thing, just make a metal coating just on above that, very thin, so that light can come out of that small hole, and then a metal, or you can also drill hole through that metal particles, but metal particles should be nearby to that hole. If you see that, then light will be even slower, but light will be even slower, and it will bend, it become nonlinear. As you know that surface plasmon resonance create nonlinearity in the light frequency, and in the nonlinearity will, and also not only that, in this principle you can make the light so small, even eventually you can see an atom. But the fun is that you can make it slow light and can go to the perfect lens. This is called super lens, that you can actually make a silver nanoparticles or gold nanoparticles and go to that. But intensity will, because scattering will be so high, intensity or absorption, scattering will be so high that the intensity will be so low that you cannot see even few nanometers, forget about atom. So that's why super lens, it is theoretical, but you reaching to that limit is difficult. So there only CMET is working in the one of the, I will not say they are the pioneer of this subject, this will be lie, but they are working in very advanced stage in this whole world. They are in the advanced stage. They have made these dielectric materials. Now, as I told you, semiconductors allows light. It does not scatter all the light. At the same time, you make the semiconductor close to, it will not be the ideal metal, close to metal. So that means this superlensing property will be there. That means it will concentrate the electromagnetic wave. At the same time, they will tell, okay, why you can go also some part. So intensity, keeping intensity intact or somewhat visible, where you can do other manipulation to make it better for your analysis, if not for the effect. For your analysis, you can make it perfect. At the same time, you can focus it to the lower. So this is the area which is going to enrich with time. We are in the very, very primary stage. We are utilizing or when the whole world in the very primary stage of utilizing the super lensing using the wide band gap material. And then also, and one day we hope that we can, instead of TEM, a normal TEM, I'm not going to do it, HRTEM, in the or even the HRTM level we can reach by using light. So you can understand how life will be easy and cheap. Nowadays, the biologists are studying their objects, sitting in the, dynamically they are seeing the bacteriophage activities using this microscopy, 4-pi microscopy or different microscopies have developed. In fact, 2014, it got Nobel Prize for that purpose, for that reason. Next, please. Okay, that's what I was talking. When you reduce the size of this, now you go to the next, because it will be difficult. Here you can, that's what exactly I was telling you. You can make a metal and dielectric, the silicon as a dielectric PMMM, and it is silicon is for a support material only. So PMMM and then the metal, if it is kept close together, then you can see a 30 nanometer, that means 300 angstrom hole you can send 300 angstrom. Remember, that means 30 nanometer hole is sufficient to send light. And this was done in 1984. In fact, he is an Indian Jews, now presently in Israel. Aaron Lewis, actually his student Betty, who got the Nobel Prize in 2014. Next, please. So I will not go to the calculation. Now we see lambda by 2, how if the transparency can be taken, lambda by 2, actually, if we manipulate it, if we can manipulate it, we can go to the lambda by 4 pi. That means lambda by 16 very easily by uncertainty principle and all those things. Next, please. So I will not go into that. And now you can see, you can focus the light. As I told you, this will be mostly example, or I can spend some time. You go back to the previous transparency. So I think I have some time. See, you know the uncertainty principle, that uncertainty in position and the momentum cannot be greater than h cross by 2. Now, if you replace the momentum value with the, so it is obstructing everybody is living and is obstructing. Yes. So delta x it will be 2 by, and you know momentum vector is equal to momentum by h cross. And now if you delta, it will be 2 by the momentum kx, particular direction, one direction we are talking, kx, and is the momentum, lambda 2 pi by lambda momentum vector. So this 2 pi by lambda, if you place it here, so it will be lambda by 4 pi. So now if you send for positional moment uncertainty can be taken from lambda by 2 from the Abbe's uncertainty to lambda by 4 pi, so lambda by 16. So you can understand now, suppose you have a 100 nanometer, 500 nanometer. Earlier it was 250 was the limit. Now 250 can be divided by 16. So roughly 20 nanometer you can think of, right? Or around that 30 nanometer. So you can easily, in fact, and a matter of fact, very easily you can reach 10 nanometer. If you use up a particular geometry in between, putting dielectrics and all those things. So those are all engineering things, but to understand the physics, that is the part. Next, please. I'll ramp through. So now if you see, you can make a lens out of gold nanoparticles. You see gold dots are given in a convex shape. You can take your own shape or your own idea and just can focus it, and you can pass it through a hole which is also made of gold, which is another concentrator gold strip, and in a particular things, and this is a submicron level hole. You can send light through that. So that means you can focus the light to that level. You can see the number B of this at the top corner. You can use the light of earlier without plasmonics you can go this much. This is the width, but with plasmonics you can make it so narrow. That means you can make a focused. You can focus the light farther. Now next please. And this is beautifully used as, I don't know whether people know it about it, but I always give this example that you have a CD. Earlier you used to record for a movie, you used to have more than one CD, or that time DVD was not there. But when the question of DVD came, when you can record 6 movies in a particular CD. Okay, I'll not name it DVD, I'll call it again CD in a different modified. In the same area, you are now making 6 movies. How you can do it? You can focus the light better, as I give you the same example here. So here the FWHM is 80 nanometer, 90 nanometer, and earlier without any silver. What they use in the CD, as you know, CD structure, I'll not tell it, the recording principle. The one layer they put silver where the light is more focused, and it can be focused up to 90 nanometer. Earlier it was 320. This is all lab example. Now engineers can do even more marvel. So 300 nanometer to 50 nanometer, I'll just go in the order. So one order less focusing area, that means one order higher recording capability. You understand, no? You record with the light being focused in a particular spot, either changing its phase or changing its re-recordable is basically the material used as changing its phase, and not once writing means something which is engraving one groove so that the reflection from that point comes in. So that subject you read it, how it is used. So there you can find out that how focusing light it has reached to the poorest of the. Now a farmer or a simple school boy is going and asking, no, uncle, you give me a DVD or you give me this because I want to record more. I want to store more data. So they, without understanding the subject, each has gone to that level. Next, please. Okay, so now we are talking of SARS, or I give an example of SARS where you have to inject a large number of carrier to the system. But if somebody is not interested, that I don't want to give too much of gold, and as I told you, but I didn't come to the subject very fast to develop this. Now, what you can do, you can, as you know, that AFM is a technique which can probe an atom. Very good. Now, if AFM can easily in the lab, people can see even in the normal atmosphere, if you making the humidity condition very good and your sample preparation is very good, you can see an atom. That is plenty of examples are there. Very well, you can see in the atoms, of course in graphene, otherwise also in some acetylene molecule have been imaged by the normal condition. So you don't have to pay very heavily. So now it only requires certain experience. Now, what you do is that if you buy a metal tip, that is also available with little bit of one gold either coating on the both side or a gold nanoparticle attached to the tip of it. It is available commercially, very well and very cheap. Now you have to make some arrangement for doing your light scattering experiment. If you can do that light scattering experiment by a commercial system, nowadays handheld systems are, everybody is selling. Every day Delhi IIT is making. You can contact any, now presently we are going to buy one handheld Raman, which was earlier some 40-50 lakh. Or 30 lakh. Now we are getting Indian market 15 lakh very easily. That means the RRCAT is making. So you can make a handheld Raman. And if you can couple it with this commercial AFM system, which you have in the lab, which are also not very costly, funded by even each and individual laboratories. If you are intelligent and if you can couple it with a fiber optic, you can make your TARS. You can observe atom. I'm telling you, this is the kind of imagination or the promise I'm making to you. Here it is a simple RNA. As you know, RNA is very popular nowadays. Everybody knows what is RNA and DNA. It can be imaged. It can be not. It is not an image of a RNA, but I'm not telling that promise. But at least in the atmospheric condition, you can study a RNA. What is the component of the RNA, and from that you can tell what is how you can identify the particular virus or particular whatever RNA about it. As you know, RNA is too much troubling us nowadays. So simply virus can be detected or identified by a locally made. If somebody is entrepreneur, I know there are a lot of entrepreneurs sitting out there and future entrepreneurs, they can make it commercialized and bring it to the home, means at least to the normal laboratories. You can imagine that way. So this is the typical image. This is called T-enhanced Raman spectroscopy. It's very big name. People are very psyched about it, and probably I am the only person in India who can do TARS, but Sivasan is one of the experts. But interestingly, it is not. Interestingly, it is not so difficult. You can do it. You just can think about it. So you can do so that means you are non-invasive. You are not putting too much of the impurity in the system. You are taking close to the tumor. Of course, if it is inside the body, it will be difficult. But if it can be extracted, a sample can be extracted from there, which is easily possible by a non-invasive way. You can take a sample out of it and you can just do this study without putting any gold nanoparticles, so that people can ask questions. Oh, you have damaged the system. This is not the actually in situ study, in vitro study. You know, biology people are very, very cautious. They will not allow any inclusion. The in vitro, in silico, all kind of terminology came for that. So in vitro studies, if they don't do it, you can do this study where the metal particle does not hamper the biological tumor, because they are all interactive. You know, tumor, if you just put a gold nanoparticle, is interacting with that. They're all what is wrong about that. So this is next, please. So, and in this technique, you can increase the electromagnetic wave even more than for the SARS. You can that you read the subject paper, it will be very easily told, but nevertheless, you can get a proper correct. It is a strain measurement in a CL nanowire because of the bending and all. The Raman keeps the strain measurement. There's too much physics. We are not talking physics here today. So you can do a lot of physics. Next. Yeah. So now I'm going to this. Okay. Next. This is we are already crossed. Yeah, here it is example. Again, I will not have time to do this, but here a single molecule is imaged. Now, single molecule image is very careful. It cannot be done in room temperature. It requires cost effective because a molecule has to be stable. So we have to go to the low temperature. That facility we are trying to create now in our lab. And this is not there in India, and only few places in the world is having. Maybe only 1 or 2 places are there where you can do very low, ultra low temperature. What is the utility of it? The utility will be more in the understanding the catalytic activities of a molecule used in the chemical industry very much. Because Raman is Raman can give you perfect analysis of a chemical activity by spectroscopic technique. So it is a typical example. It's a nature paper. You can understand very well read it like that. Where molecule can be also studied. Next, please. I will not talk. This is a machine which I have worked. It doesn't matter. This is the different example how you can do. Already I told it that how near field measurements can be done and all those things. Next, please. Here is the example. This is actually Sivadas and so on, where you can even see gold nanoparticles. You see gold is the absorption. So 532 nanometer. That is, it is the ENSOM image, near field image, where you can see even 10 nanometer gold nanoparticles absorbing the light. Next. You skip. This is a silicon nanowire. This is a silicon nanowire of 25 nanometer. We image for the first time. Next. 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 This is 25 nanometer. Next. 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 Okay, you stay here. No. Next. Previous one you could have here. Okay, so now previous, yes. Okay. So now you see, if you make you have seen many colors in the nature, right? It is a beetle. Normally, beautiful beetles are there in the all around us. Actually, I wanted to show something else, but doesn't matter. Now, if you can make a dielectric material, in fact, dielectric material of different dielectric properties, if you can make a periodic arrangement in 2D or in 3D or 1D or 2D or in 3D, then what you can do is, as you can understand, if you look at it 3D and you think that each block, yellow and red, has two different, yellow has a space and red has two different materials. It's just like a crystal. If you think of a crystal, say it is like a FCC crystal. Simple cubic system, if you think of. Analogous to the electronic materials, this optical materials also, like I told yesterday, we told that a metal in a crystal will kind of form a band. We didn't tell it, but everybody knows that they form a band, that is conduction band and this thing. Here also, if you can make dielectric materials in periodic way into 1D material, 2D material and 3D material, then you can also create a band in it's called electronic analog of optical band. Now, in this way, if you make a specific arrangement with different dielectric constant values, you can see light when you are sending, let's say a white light you are sending, only certain wavelength is being transmitted or reflected or whatever it is, or scattered. So reflected in scattering and in case of a transmitted. So whatever way you want to look at it, or whatever way you want to design your device or your observer, you can make a color, see same structure with different gap. They have created, see, this is the original structure. Now with 10 nanometer of alumina they have used, 20 nanometer of alumina, 30 nanometer of alumina, and same structure then 40 nanometer of alumina. If you do it, you create a different colors, artificial colors are made. The scattering changes with the size, that everybody knows. The sky changes its color, and as you know, sky changes its color because of the scatterer, the size of the scatterer, right? And of course, angle of the scatterer also. That is also actually here, it is there. Many people don't say it is there. I'm just telling you, it depends on the color also. Like I'll tell you one example at the end, then it will be clear to you how it is changing with the color. In the case of sky is also it is important, and in nature also it is important. I'll show you. So the color of a natural object or an artificial object created by an optical band. Optical band is created nothing by the periodic arrangement of the dielectric materials. You can see, you can give a color, not only color, there it does not end. Engineering is not very all about a color is all about impression, but engineering is you can bend the light. That means you can make optical engineering by making light in a particular path by particular defect created in a dielectric structure. So they make a defect, deliberate defect in this, so that they split the light in two different, is a natural beam splitter and all kind of things. These are all natural nature object in the nature use it, and now engineers can do it. This is called photonic band gap. And the color of the beetle is because of this different arrangement of these particles. Mostly I'll not say, and also when the chameleon you change their color is because of this is the way they do it. Even they change their pattern of the surface also is by this pattern, which will be known, which I'll not discuss it, but you can imagine it. What they do it, that how do they get good the signal or not? They pour different chemicals to their particular structure, and the chemicals are different dielectrics, right? With this dielectric constant, they change the color. Chameleon changes its color according to the place they are. I don't know what are the ranges available in their body, but it is very astonishing. But this is the only technique they use it. Next, please. Okay, now this is a puzzle I always tell. Before going to that puzzle, doesn't matter. That you see the right hand side of you of the transparency, not of you also, right and left hand side of the transparency or right hand side of the you. You see, this is a peacock feather. Now that is the example I was telling. Peacock feather, if you are a bird feather, if you look at it different angle, the color changes slightly. Okay, blue will not be red, but blue it changes its spectrum from deep blue to light blue. If you change your color, you see a bird is moving his neck here and there. Constantly they will do it. They are very restless people. So restless creature. So if they do it, and you see the blue is changing sometimes very dark blue to very light blue. So that means these structures, which are finally, it is now sure, I have not given the puzzle. The left hand side corresponds to one of the structure in the right hand side. Now Professor Potty can click one click. You see, this structure belongs to butterfly. All these colors of beautiful colors of butterfly comes from a rod-like structure. Okay, next. That is the final inside image you can see. Here it is peacock. Peacock is also rod with a different dielectric perhaps. That's why they are very close to each other. Now this is a motor structure. That is a motor and cell structure. That means it's like a bricks. So this is a brick structure, which is a very very strengthy structure in the snail or the sea creatures. Next, and this is of course belongs to next belongs to the bird, that small dot structure, and this is what we are now creating in our lab using our focused ion beam. We'll come up with a idea that angle change and all. We are optimizing this angle change and all in our, and in fact this is for your information. I'm already very late. This is already Lego is making toys, making this left hand side principle by different structure, so that chemicals are not used for coloring, which is harmful for the kids, but they will be very costly. Next, please. I think that is the last but one transparency. That is the metamaterial. It is metamaterial is, I'm only showing you the negative refraction. You see light normally if you goes into the different refractive index media, it should either come close to the normal axis or go close to this for total internal reflection. You can, if it is a heavier refractive index, higher refractive index, it can go towards the you can make a what do you call total internal reflection or a refracting material. But nowadays we make the structures, if just this layer structures, 2D array. It is not that example of that always. A 2D array of different dielectric constant material, which is actually cement is making now, we can have a negative refraction. So negative, it will go in the same axis. That means you can think of, you are using dielectric, that means as if light is getting reflected. Right? Light is getting reflected in different refractive index media. That is very interesting. Earlier, the light can be reflected in the same refractive index media, so there is no problem. So that means light will be of different. If it is different refractive index material, light goes through. You understand its velocity is different, right? So its frequency is different. So light is going in, light is coming out, but interestingly, the light wavelength has changed. So now, not only these metamaterials are now, in fact, we are planning some experiment. Maybe in future we can club with CMET. That is, we are trying to make even a micro cantilever which will be made of metamaterial, where you can bend it. You can bend a cantilever, like you see your silicon tip or something. No, if you mishandle it, whoever has handled AFM tip, you mishandle it, breaks. Immediately it breaks. We are trying to make a AFM tip. Of course, it will be a limited issues at this moment, which will not bend. You bend any amount, like a spring, it will come, it will go up. So same metamaterials are used in the engineering for anti-seismic, large seismic vibration. They can take care of it. Many other things. Metamaterial is something. Meta is a different regime. I told you. It was not ever thought before this plasmonics or all this other design came in the idea. Okay, all these nanostructure came. Next. So that's what I've already taken your discussion time. I'm sorry, but I think I had to go about it. Otherwise, the subject cannot be made understood to others. Earlier, I used to run, and then I used to have a bad feeling that people have not understood it. That is not correct. So there's three part I have this. One is confining light, then photonic band gap, and then the metamaterial.